acceleration, we now have angular acceleration. Right? We also have that the sum of the torques as a vector is equal to change in L with respect to time, which is change in angular momentum. We're going to get to angular momentum in just a little bit. But if you recall, if we recall backward, if we go back to, we went back to momentum a little while ago, recall that the sum of the forces is equal to change in momentum with respect to time. So dp dt. Sum of the forces is equal to dp dt, so the sum of the torques is equal to dl dt. So the derivative. All right, and so graphically, what do we mean by torque? Well, if I have some object, say it has some length, right, and here is my axis of rotation over here, and I exert some force on that object. So here's my F vector. It's getting a little messy. F vector. Right? Then my R vector is drawn from the axis of rotation to the point at which the force acts. And if this is the situation, what is the direction of torque? From your perspective? Out of the screen. It's the right-hand rule, right? I point my fingers in the direction of R, and then I curl towards F, and my thumb points out of the screen. That's the direction of the torque. All right, so I use the right-hand rule again for the torque because it's the cross product of two vectors. The same way that we have used the cross product before. Okay, so now we actually need a modification of kinetic energy. Because kinetic energy is no longer just translation through the air. We also, besides this 1/2 mv of my center of mass squared, I should make this big M for the total mass of the system. I have to add also 1/2 I around the center of mass, omega squared. So this is for translation, and this is for rotation. And each of these terms contributes to the kinetic energy. So I can have a total kinetic energy, which has both translation and rotation. And so I can also relate torque to work. And so because we've substituted torque for force and we've substituted angle for position, you can guess where this is going. Torque is really just the integral between two angles of whatever that torque is integrated over some angle d theta. Or over that angular direction d theta. Excuse me. We also have power in rotational motion, which can be given by P is equal to torque times omega, just as we have P is equal to F delta V. This doesn't violate the fact that these are, and I didn't draw tau and omega as vectors, right? Because in this case, we don't have to worry about the dot product because, well, you do technically, all right, but I'm not going to ever give you a situation where the torque acting on some object is not in the same direction or the exact opposite direction as the angular velocity. Okay, so it's either going to be opposing the angular velocity or contributing to the angular velocity. I'm not going to give you something where torque and angular velocity are at something. You can have that, but we're not going to do that. Okay, so really, these shouldn't be vectors. But in terms of working it out in a problem, I'm not going to give you the vector product of tau and, or excuse me, the dot product of tau and omega. Okay. So I said we're going to get to angular momentum. Let's get to it. So angular momentum L is given by R crossed with P. So this is for a particle. So for an individual particle that we can treat as a point mass, right? We have some radius from the axis of rotation. So we draw a vector from the axis of rotation to the particle. That's our R vector. And then we have some velocity vector of that particle. What direction is it traveling in? At what speed? Right? And we take the cross product of those two vectors, and that gives us the angular velocity vector. Okay, which is again, we again use the right angle to determine direction. Now, for an extended object, the angular velocity is the moment of inertia times the angular velocity. So this is for a rigid, extended object. Okay. All right, so let's spend a little bit of time. We've got about 12 minutes remaining. I'm going to try to get to as much as I can. I want to spend just a little bit of time talking about equilibrium conditions. Because a lot of people have problems with that, probably on exam 2 as well. So our equilibrium conditions for some of the forces are equal to 0, so in other words, Newton's first law, and also the sum of the torques is equal to 0. So what that means is, right, I can have something that's either at rest, or it's traveling at some constant velocity, or I have something that's either not rotating at all, has 0 angular velocity, or it's rotating at a constant rate. Right? That's what each of those conditions means. Right? If the sum of the forces is equal to 0, there's no acceleration. If the sum of the torques is equal to 0, there's no angular acceleration. Right? Most of the time, we talk about things as having v is equal to 0 and alpha is equal to 0. But they could, or excuse me, v is equal to 0 and omega is equal to 0. But they could have some v and omega with these conditions. And so, for example, an example of an equilibrium condition problem, I'll just take the one that came directly from the exam. Right? We had some point P over here. We had a sign hanging off of this beam, and then we had some cable that was supporting the beam with some tension. Right? So in a problem like this, if I give you another problem like this, and I almost guarantee that I will give you another problem like this, what you need to do in order to set up the problem is to draw a force diagram. Now this is a little bit different than a free body diagram, because in a free body diagram, we represent our object as a point, right? And then we draw all the forces acting. In this situation, we have some large extended object, and we can't just treat it as a point because the forces are acting at different points along this object, right? So if I wanted to figure out what's happening to this bar, and I wanted to set up this problem, I would draw it as a bar, right? And then I would draw each of the forces acting on that bar. So over here, I've got the tension acting down due to the weight of the sign, which is really just equal to the weight of the sign. At the center of the bar, I can treat all the mass as though it's the center of the bar, and acting downwards. So this is the weight of the beam. That's acting downwards. I've got this tension, which is holding up the beam. And so that tension is acting in this direction, right? Along the direction of my cable. Let me just label these things. And then at point P, over here, I have some other force. And so we can reason out, without even doing any of the math of setting up the equilibrium conditions and then putting in the various forces, and then maybe breaking up force into x and y direction and figuring out all the torques, we can figure out the directions, if not the magnitudes, of the forces at P, due to the fact that we have these other forces, if we just think about these equilibrium conditions. All right? So we're saying that this beam is at rest. It's not rotating and it's not accelerating in any direction. So we can say that, therefore, the sum of the forces has to be equal to 0, and therefore there must be a horizontal force acting over to the right, because there's a component of the tension which is acting over to the left. So there must be a component at P acting over to the right to balance that out. So there's got to be some force acting in this direction. And at the same time, I know that there must be another force as well, because if I consider the sum of the torques being equal to 0, I can choose a convenient axis of rotation. And if I choose my axis of rotation to be at the center of the bar, right, then what that does, remember back up to the top, torque is equal to R cross F, right? If R is equal to 0 for both the tension and the weight of the beam, then those two forces don't contribute to the torque at the center of the bar, right? If I choose that to be my axis of rotation. And so therefore, I've only got one force that is contributing to the torque. This horizontal force acting from P back to the right doesn't provide any torque on the bar because the angle between R and F is 0. And the angle between R and F is 0, I get RF sine theta, sine of 0 gives me 0. There's no torque due to a force acting along a direction that goes through the axis of rotation. So this one doesn't contribute to torque, but this one does contribute to torque, right? And so if some of the torques is equal to 0, I have to have another force which acts downwards to balance that out, to prevent this bar from rotating, right? Because this force over here is going to tend to rotate it downwards, or it's going to tend to rotate it, in the clockwise direction. So I have to have a force that's going to tend to rotate it in the counterclockwise direction to balance that out in order for the sum of the torques to be equal to 0. So I didn't ask you for that vertical force in the problem on the exam, but you could reason it out just based on this kind of reasoning, and then you can do it out mathematically as well. So, what's up? There could be a case where that goes up. If, for instance, maybe the tension on the, it depends. Yeah, it depends on, there could be a case where it goes up. Say, for instance, if I have the tension acting on this cable is not at the center, and maybe the tension is acting in some position that's further out, then I could potentially have a force that acts up here. Okay? All right. But that would depend on the magnitude of the forces. I'm not going to get into that kind of detail. But yeah, you have to figure out, depending on the magnitudes of the forces. But in this particular case, you can reason it out. You won't always be able to reason it out. The important point is to choose a convenient axis of rotation, which allows me to eliminate a couple of these forces when I'm thinking about some of the torques. Okay. All right, so we don't have too much time left. I'm going to try to push forward and see how much we can get to in that time. So we have tensile and compressive stress, which is equal to Young's modulus, which is a constant, which gives us the perpendicular force acting on some object times its initial over the area of that cross section times some change in length. So this is Young's modulus. This is again an idealized situation for just a limited amount, right? If we exert some certain forces on some object, eventually they're going to break. We go up to some large amount, but for some small range of forces we can narrow. All right, so say for instance we have some object that has some length L0, right? And then we exert some force on it, some tension on it. F perpendicular, which is the same in both directions, and it changes in length by delta L. All right, so that's one situation. Or alternatively, we could exert some force on it in the opposite direction. So some compressive force on it in the perpendicular direction, and then it may change again by some delta L. All right, so those are the two different situations basically for tensile and compressive stress. We also have pressure. We learned that pressure is equal to P, and P is equal to the perpendicular force over the area.